All right, so now we can introduce what is known as the method of false position, which is conceptually quite similar to the bisection method, but instead of using the midpoint, it uses a slightly different estimate. Okay, so this is the method of false position. And the basic idea, if you will, is that whereas in the bisection method, what happens is the following, right? So if you have a function, you have some interval a to b, and the function changes value, right? Then all that the bisection method does is to use the fact that the function changes sign. It doesn't look at the function, it doesn't look at the magnitude of the function value at a or b. It just looks at the sign of it. So imagine a situation where what happens is, you have something like this, right? So in one case, the function value in absolute value is very large, and the other one is very small. You might imagine that instead of using the midpoint as your estimate for the root, you might want to do something a little bit trickier, like replace that function f by the sort of the secant line which connects sort of these 2 points, and then look at the root of that secant line and use that as your estimate. Okay, so the idea then is to choose the x-intercept of the secant line sort of joining a comma f of a and b comma f of b. All right, and you can check that that point, which I call alpha n, is b minus f at b, b minus a over f of b minus f of a. Okay, all right, and that's really just a little bit of manipulation, which I won't spend too much time going into. In any case, you can use this then as an alternative estimate instead of the midpoint. You can use it's like this false position in some sense, and construct an algorithm accordingly. So let me sort of say, let me just state the algorithm. So much of it is very similar to the bisection method. So this is false position. Right, so your inputs are the same. You want f of x, you want a, b, you want a tolerance, and you want the maximum iteration, and the output is alpha n and the number of iterations n. And then you still have to check that if f of a times f of b is greater than or equal to 0, then you stop. Right, and then you let n equals to 0 and m stop equals to 0. So all that's really the same. In fact, the only thing which is different is, well, there's sort of two things which are different. One of which has to do with what alpha n is, right? So instead of alpha n being the midpoint of the interval a to b, you have this other more complicated expression. But the other thing which changes then is the absolute error stopping criterion, right? Because now, because of this thing, alpha n is potentially anywhere it's like an interval from a to b. So the absolute error, which is guaranteed, is only actually b minus a, not b minus a over 2. All right, so that changes the stopping criterion a little bit, okay, by a factor of 2. So anyway, so n is equal to n plus 1. Alpha n is whatever that is. So that's b minus f of b, b minus a over fb plus or minus fa. Okay, and then the rest of the logic is the same. If f a dot f alpha n is less than 0, well, okay, so let me sort of just put the tolerance condition first. If b minus a is less than the tolerance, so in the bisection method, it would have been b minus a over 2 is less than tolerance. Here it's only b minus a over b minus a is less than tolerance. And f alpha n is less than the tolerance. Well, you should have absolute values, right? Then m stop equals to 1. And then if f a dot f alpha n is less than 0, then a equals to a, b equals to alpha n, else a equals to alpha n, b is equal to b, and then you end. Oh, I'm sorry, there's a while statement here. So while n is less than or equal to n, and m stop is equal to 0, you do the following. Okay, yeah, so you end the while loop here. Okay, so again, this is very, very similar to the bisection method. The main difference again is what you use for alpha n, and the stopping criterion is changed because the guaranteed estimate now is only that the error at the nth, it's like the error is basically given by, in the worst case, it's like the interval length of the subinterval. Okay. All right. So I should remark that this is sometimes better than bisection on some problems, but in general, it's not much faster. Okay. So sometimes better than bisection, but in general, it is not much faster. In fact, it sometimes can be much slower because, you're no longer guaranteed that the interval, it's like shrinks by a factor of 2, it's like every time, right? So because the interval you have, it's like is sort of unequal. It's like, and depending on the sign of the function, it's like you'll pick one or the other. So it's not so obvious how the interval lengths change. It's like with each iteration. Anyhow, so those are sort of methods which, it's like have certain nice convergence properties. But the next thing we're going to do is to talk about methods which are faster than this sort of linear rate of convergence, basically. All right, so let me just stop here for now.